So there are a couple of other methods that the book talks about. There are many methods, of course, in the literature, but a couple that the book points out. Control variate I just discussed, and a very common application is between Asian and American options. It's also used as an application in pricing American options using European options. So that if I know, for example, the difference between the value of an American and a European option of an American and a European option in a simple contract, and use that in a control variate to convert a complicated contract European price to an American price. So you can imagine various ways in which, you know, you might just say, well, the difference between an American and a European option, you know, that's part of a control. And if I know that difference in a simple contract, maybe I can use that as an error estimate for the difference between European and an American option on a complicated contract. And then I just estimate the European values and adjust them to the American values. Antithetic is another interesting procedure which reduces the standard error in the estimate. And the basic idea of antithetic is as follows. It basically means that, imagine that we were generating either a binomial path of prices or a normal path of prices. So imagine that I generated a normal path of prices where I have Z1, Z2, Z3. Now, they're all written as positive variables, but of course, these are just normal variates, and they could be positive or negative. What antithetic does is it flips each one of these estimates through the origin. So the antithetic path would be minus Z1, minus Z2, minus Z3. So in other words, if Z1 were a positive, so if I had, for example, 1.0 minus 0.5, 1.2, then I'd flip that to be minus 1.0 plus 0.5 minus 1.2. So antithetic is a way of just producing the equal and opposite path that you did. Similarly, if I had a binomial path, a binomial lattice path, where I created a sequence and my sequence was up, down, up, then the antithetic path would be down, up, down. And I would use both paths in my sample. So what's happening is that with every path you generate randomly, you add a path which is opposite, and the opposites, in a sense, tend to force the averaging closer to the middle point. It's closer to the average. And it reduces the standard error. Stratified sampling is the last method discussed in the chapter, and this is a way of doing a better job getting a random sample. So imagine that you're trying to do a random sample from 0 to 1. It might be difficult to, you might think, to get values that really fill in. You generate 1,000 uniform random variates between 0 and 1. You might not be satisfied that those 1,000 values, in fact, give you the complete range from 0 all the way to 1. And of course, you want that for various applications that I discussed earlier. Now, one approach is stratified sampling, and here's the way we would do it. Imagine that I generated only 100 of these random variables, just 100. What this stratified sampling will do is put each one of these into a 1% cell. It'll take R1. So imagine that what I'm going to do is I'm going to break up this interval into 100 parts. So the first one goes from 0 to 0.01, then 0.02, 0.03, and so forth. And instead of taking these 100 R values and just letting them be anywhere in that interval, I'm going to take the first R value and scale it and force it to be in this first interval. And I'm going to do that by taking it, dividing it by 100. And what does that do? If Rj is in between 0 and 1, then obviously Rj over 100 is in between 0 and 1 over 100. So and then with j equal 1, that second term does nothing. Then I take R2, I do the same thing. I divide it by 100 and add 1/100th. That puts it in the second interval. I take R3, divide it by 100, add 2/100ths. That puts it in the third interval. And so you can see what I've done is taken a sampling of 100 values and made sure that I had at least one in every 1 percentile interval of the uniform distribution. And in my original 100 sample, I may not have had any in the far ends. I may not have had any in some of these 1 percentiles. And you can well imagine how this would generalize if you were going to generate a sample of 1,000. You could do the same thing by converting the interval into 1,000. Divide each R value by 1,000 and add j minus 1 over 1,000. Or you could just generate 10 R's for each one of these 10 intervals. Take the first 10 R's and use the formula here for j equal 1. The second, so that you can see there are many, many ways, and you can well appreciate that any of these stratified methods, because it forces the random variables to really fill in all of the plots there, that this would be very useful for any application where the uniform distribution were valuable, especially the application where we take uniform variables and we do the distribution function inverse. Because in fact, if I don't have a collection of uniformly distributive R's that well represents the full range of the uniform distribution, then when I do the inverse cumulative distribution that we saw earlier, I am not going to have a good representation from the F distribution that I'm seeking to reproduce. So, this is a procedure that can be used in any application where I need a good uniform. This is a way of improving the uniform distribution that I generate, and that is especially important when I'm trying to get a really complete distribution of F values using the inverse distribution function.